Ever wondered how your computer juggles a dozen apps without breaking a sweat? Or how your smartphone knows to pause your music when a call comes in? Meet the invisible maestro of the digital world, the operating system. It's the silent conductor orchestrating every beep, click, and swipe on your devices. Today, we'll peek behind the curtain and uncover its secrets. Ready to see the magic happen? Let's dive in. But first, if you're excited to join our tech-savvy club, smash that subscribe button. And if you're feeling generous, give this video a thumbs up. Don't worry, our OS overlords won't be offended if you don't. Alright, now let's unravel the mysteries of the digital universe.
That was a very fascinating intro. We welcome you to our exploration of operating system concepts. Today, we'll be taking a journey through the core ideas that power our digital world. Here's what we'll cover. We'll start with an overview of operating systems, understanding their role as the conductors of our computing orchestra. Then we'll dive into process management, exploring how our computers juggle multiple tasks with processes and threads. Next, we'll unpack concurrency concepts, learning about critical sections and the tools like semaphores and locks that manage shared resources. This leads us to the challenges of synchronization, where we'll encounter deadlocks, race conditions, and other hurdles of concurrent computing. We'll then explore memory management, discovering how our computers efficiently use and allocate their resources. Finally, we'll look at system architecture, understanding how applications interact with the operating system through system calls, and the crucial role of the kernel. In this presentation, we'll cover each operating system concept using a four-part approach. We'll start with a thorough explanation to ensure you understand the core idea. Then we'll provide a concise definition to solidify your knowledge. To demonstrate real-world relevance, we'll share practical examples of how each concept is applied in actual systems. Finally, we'll use analogies to relate these technical concepts to everyday experiences, making them more accessible and memorable. This structured format is crucial because it helps you not only grasp the theoretical aspects of operating systems, but also understand their practical applications. By the end of this presentation, you'll have a comprehensive understanding of the fundamental concepts that drive operating systems. Let's begin our journey. An operating system, or OS, is like the conductor of a complex orchestra. It's the software that manages all the hardware and software resources of your computer. Think of it as the mastermind behind the scenes, coordinating everything that happens in your device. The OS acts as a bridge between your applications and the hardware. Without it, your apps wouldn't know how to talk to your computer's components. It handles tasks like managing memory, processing data, and controlling peripherals. Examples of operating systems you might be familiar with include Windows, macOS, Linux, Android, and iOS. Each has its own unique features, but they all serve the same fundamental purpose: to make your device usable and efficient. The OS provides a user interface, allowing you to interact with your computer through graphical elements or command lines. It also ensures security, manages files, and allocates resources to different programs. In essence, the OS is the foundation upon which all other software runs. It's what turns a bunch of electronic components into a functional, user-friendly device. Concurrency and parallelism are two approaches to handling multiple tasks, but they work in different ways. Let's break them down. Concurrency is like a parent multitasking household chores. Imagine folding laundry, then pausing to answer the phone, then returning to laundry. It's about dealing with multiple tasks by switching between them. Parallelism, on the other hand, is like a team of cleaners tackling different rooms at once. It's about literally doing multiple things simultaneously. In computing, concurrency often happens on a single core CPU, rapidly switching between tasks to give the illusion of simultaneous execution. Parallelism requires multiple cores or processors to truly execute tasks at the same time. Concurrency is about structure, organizing your program to handle multiple tasks efficiently. Parallelism is about execution, actually performing multiple computations at once. A concurrent system can make progress on multiple tasks, even if it's only processing one at any given moment. A parallel system is actually working on multiple tasks at the exact same time. Understanding the difference is crucial for designing efficient systems, especially as multi-core processors become more common in our devices. Atomic operations are like taking a snapshot. They happen in an instant, without any possibility of interruption. In computing, an atomic operation is an action that completes in a single step from the perspective of other threads or processes. The key characteristic of an atomic operation is that it's indivisible. It either happens completely or doesn't happen at all. There's no in-between state that other parts of the system can observe. Examples of atomic operations include reading or writing a single memory location on many hardware platforms. These operations are guaranteed to be atomic by the hardware itself. Atomic operations are crucial for maintaining data consistency in multi-threaded environments. They prevent scenarios where two threads might interfere with each other while accessing shared data. For instance, incrementing a counter might seem simple, but without atomicity it could lead to race conditions. An atomic increment ensures that reading the value, increasing it, and writing it back happens as one uninterruptible operation. Many programming languages and libraries provide atomic operations or ways to make operations atomic, such as atomic variables or compare and swap instructions. Understanding and correctly using atomic operations is essential for writing correct and efficient concurrent programs, especially in scenarios involving shared resources or synchronization between threads. Imagine a single-person bathroom in a busy restaurant. That's essentially what a critical section is in the world of operating systems. It's a part of code where a shared resource is accessed, and only one process can be there at a time. Why? Well, if multiple processes tried to update the same data simultaneously, it would be like two chefs adding salt to the same dish without communicating a recipe for disaster. To manage this, we use tools like locks or semaphores, which act like the lock on our bathroom door. The trick is to keep these sections short. Just as you wouldn't want someone hogging the bathroom during lunch rush, we don't want processes waiting too long. Properly managing critical sections is crucial for writing efficient multi-threaded applications. It's like choreographing a complex dance where every move must be precisely timed. If critical sections are like single-person bathrooms, then semaphores are the bouncers controlling access to an exclusive club. In computing, a semaphore is a variable used to control access to a common resource in a multiprocessing environment. It's like having a limited number of VIP passes to hand out. Semaphores come in two flavors: binary, one VIP pass, and counting, multiple passes. They have two main operations: wait, asking for a pass, and signal, returning a pass. They're great for managing scenarios like a printer pool in an office, a limited resource that multiple users need to access. While powerful, semaphores can be tricky to use correctly, like a bouncer trying to keep track of multiple VIP lists. That's why many modern systems use higher-level tools, but understanding semaphores is key to grasping how operating systems juggle multiple processes and resources. Locks are like the keys to our VIP rooms in the nightclub of computing. Only one guest can hold the key at a time. In the world of operating systems, a lock is a mechanism that enforces limits on access to a resource when multiple threads or processes are trying to use it concurrently. It's a simple concept. Before accessing a shared resource, a process must acquire the lock. Once it's done, it releases the lock for others to use. This ensures that only one process can access the resource at any given time, preventing data corruption or inconsistencies. However, using locks comes with challenges. If not managed properly, they can lead to problems like deadlocks. Imagine two polite people stuck at a door, each insisting the other go first, or priority inversion, where a high-priority task is indirectly preempted by a lower-priority task. Despite these challenges, locks remain a fundamental tool in concurrent programming. A mutex, short for mutual exclusion, is like a talking stick in a meeting. Only the person holding it can speak. In the realm of operating systems, a mutex is a specific type of lock that grants exclusive access to a shared resource. It's binary in nature. It's either locked or unlocked, like a simple on-off switch. When a thread acquires a mutex, it becomes the owner, and it's the only one that should release it. This ownership model helps prevent some common concurrency issues. Mutexes are particularly useful for protecting shared data structures, or ensuring exclusive access to a device. However, they need to be used carefully to avoid deadlocks. It's like being in a room where everyone needs two talking sticks to speak, but there aren't enough to go around. If not managed properly, everyone could end up silently holding one stick, waiting for another that will never come. A process is like a chef in a kitchen, working independently with their own ingredients and utensils. In the world of operating systems, a process is an instance of a computer program that is being executed. It's a fundamental concept that allows for multitasking, the illusion that multiple programs are running simultaneously, even on a single core processor. Each process has its own memory space, which includes the program code, its data, a stack, and a heap. This isolation ensures that one process can't directly interfere with another's memory, much like how each chef has their own workspace. Processes are managed by the operating system's scheduler, which allocates CPU time to different processes. They can spawn child processes, creating a hierarchical structure, and can communicate with each other through various inter-process communication (IPC) mechanisms, like chefs coordinating in a large kitchen. If a process is like a chef in a kitchen, then threads are like the chef's hands, each working on a different task but part of the same overall job. In computing, a thread is the smallest sequence of programmed instructions that can be managed independently by a scheduler. Unlike processes, threads within the same process share the same memory space. This allows for efficient communication between threads, but also requires careful synchronization to prevent conflicts. Imagine if your hands tried to chop vegetables and knead dough at the same time without coordinating. Threads are often used for concurrent operations within a single application. For example, in a word processor, one thread might handle user input, another spell checking, and another autosaving. This multi-threaded approach can significantly improve an application's performance and responsiveness, especially on multi-core processors where different threads can run on different cores simultaneously. Multithreading is like a multi-lane highway, allowing multiple vehicles, threads, to travel in the same direction simultaneously. In the world of computing, it refers to the ability of a CPU to provide multiple threads of execution concurrently. The primary goal is to improve the performance and responsiveness of applications by allowing them to do multiple things at once. This is particularly beneficial on multi-core processors, where different threads can run on different cores. Imagine a web browser loading multiple elements of a page concurrently, or a video game handling graphics, physics, and input simultaneously. However, multithreading also introduces challenges like race conditions, when threads compete for resources, and deadlocks, when threads are stuck waiting for each other. It's like adding more lanes to a highway. It can improve traffic flow, but it also requires more complex traffic management to prevent accidents. Deadlock is like a gridlock in a roundabout where each car is waiting for the one in front to move, but none can because they're all blocking each other. In computing, it occurs when two or more processes are unable to proceed because each is waiting for the other to release a resource. For a deadlock to occur, four conditions must be met simultaneously: mutual exclusion, resources can't be shared; hold and wait, processes hold resources while waiting for others; no preemption, resources can't be forcibly taken away; and circular wait, a circular chain of waiting processes. A classic example is the dining philosophers problem, where philosophers' processes need two forks, resources, to eat, but there are only as many forks as philosophers. Deadlocks can be particularly troublesome because the affected processes remain stuck indefinitely, unless there's external intervention. Strategies for dealing with deadlocks include prevention, avoidance, and detection and recovery. A race condition is like two chefs reaching for the last egg in the kitchen at the same time. The outcome depends on who's slightly faster. In computing, it occurs when the behavior of a system depends on the sequence or timing of uncontrollable events. Race conditions typically arise in concurrent or parallel programming, when multiple threads or processes access shared resources without proper synchronization. Imagine two threads trying to increment a counter. Thread A reads the value, say 5. Thread B also reads 5. Thread A increments and writes 6. Then thread B, still thinking the value is 5, also increments and writes 6. We've lost an increment. Race conditions can lead to data corruption, incorrect program behavior, and even security vulnerabilities. Preventing them involves using synchronization mechanisms like mutexes or atomic operations. It's a reminder that in the world of concurrent programming, timing is everything. If deadlocks are like a frozen traffic jam, livelocks are like two people repeatedly moving aside to let each other pass in a hallway, but always moving in the same direction. In operating systems, a livelock occurs when processes continuously change their states in response to each other, without making any real progress. Unlike deadlocks where everything stops, in livelocks, processes are actively performing operations, but these operations do nothing to move them out of their current state. Imagine two processes that keep yielding a resource to each other out of politeness, resulting in neither getting to use it. Livelocks can be even trickier to detect than deadlocks because the system appears to be running normally. Solving livelocks often involves introducing some randomness or priority system to break the symmetry of the process's behavior. It's a reminder that in concurrent programming, good intentions like always yielding to others can sometimes lead to unexpected problems. Starvation is like being stuck at the back of a buffet line that never moves forward. You can see the food, but you never get to eat. In computing, starvation occurs when a process is perpetually denied necessary resources to complete its task. This often happens to low-priority processes in the presence of high-priority ones. Imagine a low-priority print job that keeps getting bumped by incoming high-priority jobs. It might never get printed. Starvation can lead to reduced system performance and unfair resource allocation. To prevent it, operating systems use various scheduling algorithms that ensure every process gets a fair shot at resources. Techniques like aging, where a process's priority increases the longer it waits, can help combat starvation. It's a balancing act between maintaining system efficiency and ensuring fairness, much like managing a busy restaurant where you need to serve VIPs quickly without neglecting other customers. The dining philosopher's problem is like a thought experiment turned dinner party from hell. Imagine 5 philosophers sitting around a circular table, each with a plate of spaghetti and a fork between each pair of plates. To eat, a philosopher needs 2 forks, but there are only 5 forks total. This seemingly simple scenario illustrates the complexities of resource allocation and deadlock avoidance in operating systems. If each philosopher grabs the fork to their left and waits for the right fork, we have a deadlock. If they all constantly pick up and put down forks, we might have a livelock. The challenge is to design a solution that allows maximum concurrency, as many philosophers eating as possible, without risking deadlock or starvation. Various solutions involve introducing asymmetry, like having one left-handed philosopher, or using a waiter to control fork access. It's a vivid reminder that in concurrent systems, even simple scenarios can lead to complex synchronization challenges. The reader's writer's problem is like managing a popular library where some visitors want to read books, readers, while others want to update them, writers. In computing, this problem arises when multiple processes want to access shared data, but with different intentions. Some just want to read the data, while others want to modify it. The challenge is to maximize concurrent access, allowing multiple readers simultaneously, while ensuring data consistency, only one writer at a time, with no readers present. Various solutions prioritize either readers or writers, or aim for fairness between both. For example, a reader preference solution might let new readers in even if a writer is waiting, potentially leading to writer starvation. It's like deciding whether to let more people into the library to read a popular book, or closing it briefly to let someone update it. This problem highlights the trade-offs between concurrency and data integrity in shared resource scenarios. Paging is like organizing a massive library where books' data are stored in uniform-sized shelves, pages, rather than being kept intact. In computing, paging is a memory management scheme that eliminates the need for contiguous physical memory allocation. The operating system retrieves data from storage in fixed-size blocks called pages. This allows for more efficient use of both physical and virtual memory. Imagine requesting a book and receiving it as a collection of same-size chapters, regardless of the book's actual structure. The beauty of paging is that it simplifies memory allocation and reduces fragmentation. However, it can lead to overhead if a process only needs a small amount of data from a page. Modern systems often use multi-level paging schemes, like having a catalog of catalogs in our library, to manage large address spaces efficiently. Paging is a fundamental technique that enables features like virtual memory, making our computers seem to have more RAM than they physically possess. Segmentation is like organizing a house into rooms of various sizes based on their function. In the world of operating systems, segmentation is a memory management technique that divides a program's memory into segments of different sizes. Each segment corresponds to a logical division in the program, such as code, data, and stack. Unlike paging, which uses fixed-size units, segmentation allows for variable-size memory allocations that match the natural boundaries of the program. It's as if instead of forcing all your belongings into identical boxes, you could use containers that fit each item perfectly. This can lead to more intuitive memory organization and protection. However, segmentation can result in external fragmentation, like having gaps between rooms in a house that are too small to be useful. Many modern systems use a combination of segmentation and paging to get the best of both worlds: the logical organization of segmentation with the efficient memory use of paging. Fragmentation is like trying to park a bunch of different-sized cars in a parking lot. Over time, you end up with small, unusable spaces between vehicles. In computing, fragmentation occurs when memory or disk space is used inefficiently, leaving small gaps of unused space. There are two types: internal fragmentation, when allocated memory is larger than required, leaving wasted space within allocated units, and external fragmentation, when free memory is split into small blocks, none of which are large enough to satisfy a particular request. It's like having plenty of small spaces in your parking lot, but nowhere to park a bus. Fragmentation can lead to decreased performance and wasted resources. Various techniques are used to combat it, such as compaction, rearranging memory to consolidate free space, garbage collection, automatically freeing unused memory, and using memory allocation algorithms that minimize fragmentation. Managing fragmentation is a constant challenge in operating system design, balancing efficient space usage with the overhead of defragmentation processes. Memory allocation is like assigning parking spaces in a lot to different vehicles as they arrive. In computing, it's the process of reserving portions of computer memory for programs and processes to use. The operating system needs to keep track of which parts of memory are in use and which are free, much like a parking attendant managing spaces. There are various strategies for memory allocation, such as first fit, use the first available space that's big enough; best fit, use the smallest space that can accommodate the request; or worst fit, use the largest available space. Each has its pros and cons in terms of speed and efficiency. Modern systems often use more complex algorithms and may employ techniques like virtual memory to extend the available memory beyond physical limits. Efficient memory allocation is crucial for system performance. Poor allocation can lead to fragmentation, slower execution, and even program crashes. It's a constant balancing act between speed, efficiency, and preventing memory-related issues. System calls are like placing an order at a restaurant. You're requesting a service that you can't perform yourself in the kitchen. In the world of operating systems, system calls provide an interface between a process and the operating system, allowing programs to request services that require higher privileges. When a process needs to perform an operation like reading from a file or creating a new process, it makes a system call to the OS kernel. This is a crucial boundary between user space, where normal programs run, and kernel space, where the core OS functions operate. Common system calls include open, read, write, and exec. It's like having a set menu of services that the OS provides. Programs can order from this menu, but they can't go into the kitchen and cook themselves. System calls are essential for maintaining security and stability in an operating system, ensuring that user programs can't directly access or manipulate critical system resources. The kernel is like the engine of a car, essential for operation, and hidden from direct user interaction. In computing, the kernel is the core component of an operating system, acting as a bridge between applications and hardware. It's the first program loaded on startup and remains in memory to manage all other programs. The kernel handles critical tasks like process management, memory management, device drivers, and system calls. It's like the central nervous system of your computer, coordinating all the complex interactions between software and hardware. There are different types of kernels, such as monolithic kernels, where all OS services run in kernel space, and microkernels, which keep the kernel small and run most services in user space. The design of the kernel significantly impacts the overall performance, security, and functionality of the operating system. While users rarely interact with the kernel directly, its efficient operation is crucial for a smooth computing experience. As we conclude our journey through operating system concepts, let's recap the key ideas we've explored. We began with OS fundamentals, understanding the core functions of operating systems and the crucial roles of processes and threads. We then delved into concurrency, exploring how systems handle multiple tasks simultaneously through multithreading, and the importance of atomic operations in critical sections in maintaining data integrity. Our exploration of synchronization tools revealed the mechanisms used to coordinate between processes and threads, including semaphores, locks, and mutexes. We also tackled the challenges that arise in concurrent systems, such as deadlocks, race conditions, livelocks, and starvation, understanding both their causes and potential solutions. In memory management, we uncovered the strategies used to efficiently utilize computer memory, including paging, segmentation, and techniques for handling fragmentation and allocation. Finally, we touched on some advanced concepts, including classic problems like the dining philosophers, the practical importance of system calls, and the central role of the kernel in modern operating systems. These concepts form the foundation of how our computers, smartphones, and countless other devices function. By understanding them, we gain insight into the complex world operating behind the scenes of our daily technology use. As you continue to use and interact with various devices and systems, remember the intricate dance of processes, memory, and synchronization happening within. Thank you for joining me on this exploration of operating system concepts. Keep curious, keep learning, and happy computing.